All right, let's do section 9.2, page 454, number 24, which reads, identify the indeterminate form and evaluate the limit using L'Hopital's rule. And for number 24, we have the limit as x goes to 0 from the positive side of sine of x all to the x. Now we've been talking about all the different methods we have for evaluating limits, and the first one is to graph. And for whatever reason, I decided to graph this one. And when I do that, I get something that kind of looks like that. And this is right around 1. So as I approach x equals 0 from the positive side, I want to say that this limit is something like 1. But I still need to prove it analytically. Proving it graphically isn't enough. So the second thing that I'm supposed to do when I'm evaluating limits is to substitute in. So let's do that. So that means I'm going to put 0 in here, and I'm going to have the sine of 0 all to the 0, and the sine of 0 is 0. So I'm going to have 0 to the 0, and that is in fact an indeterminate form, and one part of this problem is to identify that indeterminate form. Unfortunately, this is not an indeterminate form to which I can apply L'Hopital's rule. And once again, I have L'Hopital's rule written up here in green, and it says that if we have the limit as x goes to a of f of x over g of x, and if that is equal to 0 over 0 or infinity over infinity, and f of x and g of x meet the conditions we laid out when we introduced L'Hopital's rule, then this is also going to be equal to the limit as x goes to a of f prime of x divided by g prime of x, remembering that we're taking those derivatives of the numerator and the denominator separately. So I'm going to have to manipulate this so that I can have 0 over 0 or infinity over infinity. So this is really the same situation we had in the last problem. And what we did there was to let f of x be equal to sine x to the x. And then I took my limit as x goes to 0 from the positive side of f of x, and I realized that that was going to be equal to the limit as x goes to 0 from the positive side of e to the natural log of f of x. And I can do that because e and natural log are inverse operators. They undo each other. Just like squaring something and taking the square root, I get my original answer back. So if I can solve a side trip and figure out what the limit as x goes to 0 from the positive side is of the natural log of f of x, then I can use that to solve my real problem. So let's do this. So I'm still going to have the limit as x goes to 0 from the positive side. And I'm just going to substitute in for f of x. So I'm going to have sine x to the x. And we're going to once again use that great property of natural logs, which tells me that this exponent can be brought down as a multiplication factor. So I'm going to have the natural log as x goes to 0 from the positive side of x times the natural log of sine x. Now remember again that L'Hopital's rule has a numerator and a denominator, and I need to have that too. So again, I'm going to have to be creative. I'm going to take the limit as x goes to 0 from the positive side. I'm going to leave the natural log of sine x in the top, but I'm going to move that x to the denominator as 1 over x. Well, now I need to substitute in again and see if I can recover a form that I can apply L'Hopital's rule to. So if I substitute in, then I'm basically going to have the natural log of 0, because we said that the sine of 0 was 0, over 1 over 0. And as we saw in the last problem, the natural log of 0 really approaches negative infinity, and 1 over 0 is infinity. And I've got a situation where I can apply L'Hopital's rule. So let's do that. So I'm going to have the limit again as x goes to 0 from the positive side. And remember that I'm going to apply L'Hopital's rule and take the derivative of the numerator and leave it in the numerator. So when I take the derivative of the natural log of anything, I'm going to have 1 over whatever I was taking the natural log of, so 1 over sine x times the derivative of that. And the derivative of sine x is cosine x. And then I'm going to take the derivative of 1 over x, which is going to be negative 1 over x squared, and I'm going to leave that in the denominator. Now, as we said in the last problem, a key step here is doing some algebra and rearranging things, simplifying things. So I'm still going to have my limit as x goes to 0 from the positive side. I'm going to acknowledge that this is 1 over tangent x, and then nobody likes fractions that look like that. So I'm going to switch things around here, and a denominator of a denominator is a numerator, and this tangent x is really already in the denominator. And then I'm going to substitute in. So I'm going to have 0 in the top, and what's the tangent of 0 going to be? Well, it's going to be 0. So again, I can apply L'Hopital's rule because I have an indeterminate form, 0 over 0. So I'm going to have the limit as x goes to 0 from the positive side. When I take the derivative of the numerator, I'm going to get negative 2x. And what's the derivative of tangent x? Yep, it's secant squared x. And I'm going to substitute in again. So in the numerator, I'm going to get 0. And in the denominator, what am I going to get? Well, remember what secant squared of x is equal to. It's 1 over cosine squared x. And what's the cosine of 0 going to be? 1. So this is going to be 0 over 1. So I'm really actually going to get 0. But remember that I haven't really solved my problem. I've solved part of my problem, but now I need to go back and I need to use that formula. So I'm going to extend my page here so that I have plenty of room. And I'm really trying to find the limit as x goes to 0 from the positive side of sine of x to the x. And I'm going to write that as the limit as x goes to 0 from the positive side of e to the natural log of sine x to the x. And I've already figured out that part. I know what happens to the natural log of sine x to the x. I know it goes to 0. So this is going to be e to the 0, which is equal to 1. And that agrees with what I found graphically.